In the previous subsection, we talked about periodicity, and we noted that a periodic string is repetitive, and this helps for string matching. But aperiodic strings seem not to help with string matching. So in this subsection, we will see how to make use of the fact that a string is aperiodic to also speed up or simplify the matching in our application of string matching. For that, we need another definition, and that is a witness for non-periodicity. It's again, it's a simple definition, but it's a bit of a mind-boggling game with indices. So I'll show an example in a second, but try to digest it for the moment. So we're given a pattern, just a string, and suppose it does not have a period p. So p is some number. I mean, it's clearly between 1 and n, excluding n. So it's a non-trivial period, and we say p does not have this period. So that means if I try to stick the two copies of p on each other, where I shift here by p, I must have some mismatch. So these are not the same. These two strings here, they're not identical. So that means there's some place where I find a mismatch. Okay? And this is my witness intuitively. There's a witness, there's one position that witnesses for the fact that these are not the same. So it's a witness against periodicity p. And formally, W is, okay, we want a picture here. So W formally is this position in the shifted copy. And then this is W plus P, right, in the pattern. So it's a position where the this is omega, not W. It's the Greek W, but to be consistent and fair to our Greek colleagues, I should call it by omega, because that's what it is. Even though W would make sense because it stands for witness. Nevertheless, just the name. The omega-th character in P is not the same as the omega plus p-th character, and these are exactly those two. Again, a simple definition, right? Whenever we have a non-period, there must be a mismatch somewhere along here, otherwise it would be a period. So far, so good. How can we use this for string matching? Okay, again, if a pattern does not have this period, then suppose we try to align the pattern with the text, and we try to guess there's a match at position I. Now we also shift the pattern along itself with distance p. So here again, this is p. So there could be another match at position I plus p. But if the pattern does not have period p, we cannot possibly have both. Either the position I is a starting index of a match, or I plus p, but not both, because if both were a match, we would have found p here, and we would have found p another time here, and that would mean these are all the same. That would mean p has this period, but we assume p does not have this period. Okay? So simple observation again, if you spell out the indices, there's a position. If you check the second potential occurrence, there is some mismatch here at omega, respectively omega plus p within the pattern. In the text, I have to add the offset I plus p, so that's this first part. This one can be the same as p of omega. If this were both a match starting at this, then this omega character would be aligned with that position in the text. But we know because of non-periodicity, because of this witness, that this position in the pattern is not the same as this position in the pattern. And that again, that would be this guy, which is aligned with the position in the text at I plus omega plus p, but of course these two things are the same, right? This is the same position, just written in different ways. So that cannot be the case. These are equal, but here's an unequal sign. So that would be a contradiction. So we can prove, formally a proof by contradiction shows that if the pattern does not have a period p, then at most one of those two positions can be an occurrence. That's the notion of a dual. We will let I and I plus p fight a dual, and the dual will be comparing one position in the text. And the outcome of the duel will only have one survivor. Only one of the two guesses is still alive, and the other is definitely excluded, not possible anymore. It could be that both are non-matches, by the way. The duel only says one of them dies. Cruel duels, that's how it is. And yeah, this is what I just said, and I'll use this little figure later. I want to discuss this again on a concrete example because the concept is kind of clear, but maybe you want to see this spelled out in a bit more detail to see how it really works. So the first step for string matching with duels is to compute the witness table. So that's this. That is just for all possible non-periods. I should say this, we assume here P is aperiodic. If P is periodic, then we don't have to go through this hassle. We already know that it's repetitive and we can deal with this separately. If P is, this is a capital P for pattern. If the pattern is aperiodic, that means for all the periods from 1 up to half of the length of the pattern, we find a witness against periodicity. And this is what the witness table stores. It just stores this omega that I introduced just before. So let's briefly go through this. Here's my pattern, and I shift it over by one position. So here's the pattern shifted by one. Here's the original pattern. And we see that, for example, this position is a mismatch. So this is not a period, 1 is not a period, because there's a witness against periodicity at position 0. It's 0 because here's the 0, and we have to align this with the position omega plus p, 0 plus 1. Okay? If we shift the pattern by 2, we again find there's a mismatch. And there may be different mismatches, but here's only one. And this is at position 3. So our omega for the table is 3. If we shift the pattern one more over, we actually have several mismatches, but let's just pick one. And one example is to pick omega 1. So we put that in the table. And well, this would have already been enough. We're already past half the length of the pattern, but we can continue in this case. Also, 4 is not a period. So just for sake of completeness, here's another omega. And even for 5, we find a mismatch. So we can fill one more table entry. That's the first step. Given an aperiodic pattern, you can compute all the witnesses against all the periods. Usually we only run this from 1 up to length of the pattern half rounded down, but there's no harm in doing it further if you can. One more remark. If you wanted to do this for 6, you will see that actually P has the period 6. So there's no witness against periodicity 6 because it is periodic. But we really only need it up to 3 in this example. So these are not strictly necessary for what will come later. All right, how do we use this for excluding matches in a text? So here's our example text. And let's try to find matches of our pattern in this text. initially, if we know nothing about the text, every possible position between 1 and whatever length of the text minus m. But here, there are many possible positions in this text where an occurrence of the pattern is possible. Now, we can make a duel, we can fight a duel between two of these positions, and one of the positions will necessarily die. So we have reduced the number of possibilities by 1. And by continuing with the winner of the duel and compare it to another position, we can always decide in one more duel which of the two candidates is currently the possible one. Okay, let's see how this goes. We start with the first two positions. So let's guess that the pattern starts either at position 0 or at position 1. We know that the pattern is not periodic with period 1, so not both will be possible. How do we use this fact? Well, the distance between those two is 1, so that's a p of 1. The period that we would need is 1. We don't have that period. Here's your witness against that periodicity. It's just the entry from that table. And look here, I aligned the text with the two potential matches. And you see that here's our witness. This is our omega. And now we look in the text at this very position. And the character at the position 1 is a b. Now, it happens to be equal to this one, but what's more relevant is it's not equal to a, which is the omega character in P. So that means the later shift, the one with the larger index, the 1 here, is not an occurrence. So, well, rest in peace, number 1. And we continue with 0. So we can compare 0 with the next possible shift. That's at 2. We do the same game. This time we find that our witness is further back in the text. But we magically again know we only have to look at this one symbol in the text at position 5. It's again a B, coincidence. What's more important, it's not a C, which is what we find if we look at the pattern position omega plus P. And you can check that the math works out in this case. So this is again is also position 5. So this means the earlier of the two proposed matches is not possible. That's the 0. So again, there she goes. And the survivor is number 2. So we continue with number 2 and compare it, say, with a potential match at 3. Now we have to move the pattern a little bit so that the two positions are aligned. Potential match at 2, potential match at 3. Again, the distance between those two is the potential period, but we know this is actually not a period. So we have a witness against that. The witness is here. So we check this position in the text. And that's a B, most known for not being an A. And that means the later potential match again dies. So that's the 3. And again, what remains from this is after 3 comparisons, out of the 4 potential matches that we checked at 0, 1, 2, and 3, only one remains, the one at 2. Now, if you check this here, this is not actually a match, but that's beside the point. The important lesson here was, with a single character comparison, you only check one comparison here is enough. You can exclude an entire potential match, an entire guess. Okay. So if you want to turn this into a more systematic algorithm, here's what you do. In all that follows, I will assume that the pattern is aperiodic. So what you'll have to do is you will first compute this witness table. And in the process of computing this witness table, you will either find, I found all the witnesses, and then you know it's aperiodic by definition. Or you find in this process, there is no witness against this periodicity because actually this is a period. And then you know the pattern is periodic and you do something different. You recurse on the periodic part, etc. That is beyond the scope for us today. We will only focus on aperiodic patterns. Now, then we start by setting this parameter. That's just the length rounded down. It occurs a couple of times, so I wanted a shorthand. Then you compute all the witnesses for all these non-periods. And then you do a clever thing. In the example, we just supposedly randomly just compared certain positions and let them fight a duel. What you really do is you take blocks of size mu in your text. And these are just the adjacent mu positions. And now you run mu -1 duels between those positions. You can, for example, go just left to right for this simple version. Remember, I'm still talking about the sequential algorithm for now. We'll talk about how to make it parallel in a second. Okay, in each of these blocks, all the distances, all the two positions, if I'm in such a block of size mu, so this is 0 up to mu -1, whatever two positions I pick, the distance will be at most mu. And that's important because that means we can use this distance and find a witness against periodicity. Okay? We cannot use this with arbitrarily spaced apart positions because then we would need a witness against a period that's longer than the pattern, and those can't possibly exist. But within this block, we can fight the duels. Each duel eliminates one of the mu potential guesses. So after all these duels, there's at most one left. And for each of these blocks, we then just use our sequential naive guess character by character. We check if the potential match is an actual match. That's similar to what we did with Raven Carp. So need a bit of space here. How long does this take? Well, this first step is trivial. This step, you can compute all the witnesses against periodicity or find that the pattern is actually periodic in linear time. We'll talk about this in a second a little bit more. The more interesting parts is steps 3 and 4. For step 3, we have n divided m blocks, roughly. It's actually n divided mu, but mu is m divided 2, so in big O notation, that factor of 2 doesn't make a difference. So we have n divided by m blocks. And we fight m duels, well, actually mu -1, but let's be generous. We fight m duels in each block, order m. If you multiply that together, you find that it's actually linear in the length of the text, right? Remember, the important point here is that every duel just needs a single comparison, a single character comparison between text and pattern. So every duel can be implemented in constant time. We fight m duels per block and have n divided by m blocks. That's a total of order n simple comparisons. And what remains is to do this check. So we have, again, n divided by m blocks, but checking an occurrence in the trivial way just needs m comparisons. So that's another order n comparisons for the step number 4. So one outcome of this unit is another worst case efficient string matching algorithm. Essentially is the same guarantees as Knuth-Morris-Pratt, achieved in a slightly different way. Now there's a slight catch to this in that we do have to compute the witnesses against periodicity. And as you'll see in a second, we actually use something like KMP for that. So it wouldn't be possible to simply use this and not know about KMP. You have at some point or another, you have to fight the game and dive through the details of Knuth-Morris-Pratt. But so much for the sequential algorithm on string matching by duels. As always, if you have questions on this or anything else, please use the lecture back channel or the Slido to ask your questions. Yep, those are open. If there are no questions about the sequential part, then let's look what we have to change to make this a parallel algorithm. And well, let's flip back and forth just one more time. You see, I made the font a bit smaller so that we have space to fit the second part on the slide, but the algorithm is really exactly the same. There's not really anything that I had to change here. So we do the same steps. Of course, we will have to talk about how to do these steps in parallel, but the core algorithm is still the same. And so how do we parallelize this? Well, I'm coming to the picture in a second, but let's first talk about the simple things. The first step's trivial again, just compute a number, but the second step is actually not trivial. It's actually very complicated. I'll come back a little bit to this. It turns out you can do this in time log squared m, and on some models of our machines, maybe even faster. How can we parallelize the duals within a single block? That is the main innovation or the main observation here. Previously, we would have to do one dual after the other, so we needed order mu time in total in the sequential model. But it turns out that you can do a lot of these duals independently. Suppose that your mu is, so this would be mu is equal to 8. And suppose these are your positions in the text. There's position 1, 2, etc. You can have 0 and 1 fight a duel against each other. And at the same time, 2 and 3 and 4 and 5 and 6 and 7, they're all independent. There's no data dependency. Remember, this is what I said many times before. Strong dependency in the data between one step and another is what kills parallelism, but here we don't have that. The duals that talk about different positions can run independently and nothing has to wait for the result of the others. And then we have one of the winners. So here, say 0 has 1, and here 2 has 1, and here 5, and here 7. And then you find another duel between the winners of this first round, and here the same. And again, these two are independent. There's nothing that these two depend on each other. So here, say 0, 1, and here 5. And then as a last round here, you fight another duel with the winners of these two. So it's just fighting a tournament. And here 5 is the only one that remains, but that's just an example I made up. So the important part is this is a complete binary tree. And we know the height of a binary tree is log of the number of the leaves. So this has log mu height. And you might recognize this conceptually, this idea of doing something that used to be sequential linear and now becomes logarithmic. That's very much the same as we used it for computing the sum of an array, or the prefix sums then as the second step. There we also went from an unbalanced tree to this balanced binary search tree and used all the data independence. So that is how we get the third step in log mu parallel time. And the work stayed the same, just as when we computed sums. The fourth step is actually fairly simple. You can check all the n over mu guesses in parallel. And for that, you can use what you did in the tutorials. We will talk about the tutorials later today. In tutorial 4, you actually explored exactly this step, how to check if a certain guess in the text is a match of the pattern in parallel. And well, as you will remember, it depends on the machine model what the exact result here is. Okay, so the final parallel time is log m for the matching part. That comes, it's just again, mu and m are the same in terms of big O here. And because it's inside the log, it's really, even without it, it's just a constant difference. And linear work. So this is all perfect. is perfectly fine up to the matching part. The pre-processing, though, we still have to talk about. And if we do this sequentially, you can do something similar to the KMP failure array. And maybe this is not very surprising if you think about it. We've already noticed this very, very close relation between periods and the KMP failure function. Now, the only thing that you would need here is to find these witnesses. But modifying the KMP failure function algorithm a little bit actually produces these witnesses. So you can do this in the optimal sequential time. In parallel, it becomes more complicated, and there have been substantial improvements over the first more simple method, and then using more sophisticated techniques. You can get also the pre-processing in parallel log m time and work efficient. But that technique is beyond the scope of this class. So what you're supposed to know is just that this is possible. So the state of the art for parallel string matching is you can do log m time and work efficient. And this is in fact the best you can hope for on the crew RAM, our standard model, where you allow concurrent reads, but you don't allow concurrent writes. They have to be exclusive. The lower bound essentially comes from similar arguments like for the prefix sum. There is indeed, if you go to a different machine model, if you go to the concurrent write model, even in the weak form that all the concurrent writes have to write the same value, you can do the matching part in order one time. Again, this is exactly what you do in the tutorials. But the pre-processing doesn't work in constant time. The best, well, I think it's also known that this is the best possible, so you need this log m time. But that, again, so this is just for your curiosity. I will not expect you to know this, and I will not be able to talk about these results. Okay. That brings me to the end of Unit 5 on parallel string matching. We've seen that this notion of periodicity helps us to break things into two parts. We had essentially two different algorithms, one for periodic patterns that I didn't talk about in detail, and one for aperiodic parts, where we did the how to parallelize things apart from the pre-processing. And this brought you not only a new sequential algorithm, but also a best possible parallel string matching algorithm. And I hope this teaches you that sometimes you have to look at the problem from an entirely different perspective. And then suddenly you notice something like these duels help you approach a problem very differently, and then suddenly achieve results that didn't seem possible before.